General relativity, step by step. I've been talking about geodesics, and I made the observation that a perfectly sensible way to define a geodesic path was one that, unlike this path, has got a constant tangent vector, which kind of is moving around here. So joining point A and point B, that's not straight in scare quotes, because the tangent vector is moving about. But of course there's another perfectly sensible way of defining a straight line, which is to say that the path is not as short as it might be. So it's perfectly reasonable to define a geodesic as the shortest, actually not the shortest, an extremal path between 2 points from A to B. So let's have a look at what that would look like. So the path length equals the integral from the integral from A to B, I guess, A to B, of the line element, which is just the square root of Gij. Now how quickly is this moving? Well, it's moving with speed dxi by d lambda, dxj by d lambda, and it's integrated with respect to d lambda. So I'm just going to call that the integral of f d lambda. And I want this to be minimized. It's the integral along the path. Great. Well, what I'm going to do is I'm going to choose lambda so that f equals 1. Because whatever lambda is, I can make it bigger or smaller, or I can make it its rate of change along this path faster and I've gone backwards. Along the path there, I can make this rate of change faster or slower, so that these guys here cancel out my my metric tensor. So I can make f equal 1 if I want to. And I'm going to do that because it's going to be a bit nicer. So how do we do that? How do we minimize that? Well, we go back to the Euler-Lagrange equations. Euler-Lagrange equations for calculus of variations. Calculus of variations. And what have we got? The classic form of it is d by d, this is the one I was taught anyway, d by dt of di f di x dot minus di f by di x equals 0, where f equals some function, actually I may as well write it in uppercase, function of x and x dot, and possibly other things as well, o and t possibly as well. So what have I got here? I've got my f equals the square root of gij x dot I x dot j, where x dot I equals di xi by di lambda, and lambda is chosen to make this function here f equal to 1. Okay, well I'm going to call g equals f squared, just because I can, because I know that that equals 1 as well, because f equals 1, so f squared is going to be equal to 1 as well. So what I'm going to do is I'm just going to substitute f into this f here into this equation here and see what happens. Now hopefully we'll get a nice definition for a geodesic, and we'll see that it matches the other definition I had for a geodesic in screencast 49, I think it was, where the tangent vector wasn't changing. So yeah, I'm going to stop there because this one's already gone on for longer than I intended, and I'll solve this equation in the next screencast. Stop.